Hello everybody, this is AP Chemistry final project. Our subject is Chapter 6 to Chapter 7 review, electronic structure of atoms and periodic trends. Now, the first example we're going to see is a problem that has to do with a helium atom or electron that must go from its energy levels from n equals 2 to its n equals 5. Now, a problem for this is first we need to explain what if it's gonna wait. Hold on, I get another pen. Now we have to determine if this is gonna either absorb energy or exert energy when it goes from n equals 2 to n equals 5, which is going from a lower phase to a higher one. Now, it needs to absorb energy because when it goes up, it's when it's absorbing its energy, and when it goes back down is when it exerts the photons, which is the light that we see. Now it needs, and from going from n equals 2 to n equals 5, it requires to absorb energy, because when it comes back down, it's when it's exerted, and that's the light that it exhibits. Okay.
So for the next step, what we had to find is the energy of the photon with the Bohr equation. So the Bohr equation is delta E equals negative h 1 over n1 square times 1 over n2 square. So for h, we plug in what is given to us, which is negative 2.18 times 10 to the negative 18th power.
Because it's a constant.
And we multiply that by 1 over 4 minus negative 2.18 times 10 to the negative 18 times 1 over 25. So what we get here for the final answer is negative 4.5738 times 10 to the negative 14 joules.
And that is the energy emitted by the photon.
So once we find the energy of the photon, now we have to find the frequency of the photon. To do that, we have to use the frequency equation, which is nu equals c over lambda. So we already got c, which is 6.620 times 10 to the negative 34th power over what we got for the energy for the photon, which is negative 4.578 times 10 to the negative 14th joules. So our answer is negative 1.447 times 10 to the negative 15th power. And it's in hertz.
Now, with the previous information that we have gained so far, we can now determine if it's in the visible light, of which we can see which the range is 400 all the way to 700. And this falls into 434, which would be right around here of the graph, which we would see as violet light. Violet light, because it falls into that range.
Now we will look at the atomic properties and periodic trends.
He testified.
As you can see in this beautiful table,
Yes.
as you move from left to right across the periodic table, the Z effect, which is the proton to electron attraction on electrons, increases because of an increase in
Yeah, he knows the whole.
protons with no change in its valence shells.
Okay, that's good.
Pretty simple. As you move from top to bottom
No, that makes it worth it.
of the periodic table, the Z effect acting on
We're gonna
electrons
make a little bit more effort.
decreases because of an increase in electrons,
Oh yeah, it's a wonderful idea.
meaning less proton to electron attraction. Since we have finished this whole chapter, chapter 6 and 7, now we shall look into some examples. Now, we'll have to calculate the wavelength in nanometers of the light that corresponds to an emission spectrum of neon, corresponding to a frequency of 4.34 times 10 to the 14th seconds to the negative 1. Now, for this, we will need this calculation right here. C equals lambda, then nu. But since we need to find out the wavelength, the wavelength, we're gonna have to move it into lambda equals nu over c, and this will equal 3.0 times 10 to the 8th meters per second. -1. And then 4.34 times 10 to the 14th -1. Then after you do then you multiply this times 10 nanometers, because you have to convert meters into nanometers. Over 1 meter equals 690 nanometers.
So for C, what we're trying to find is which element is most metallic in character. So we got, according to this table, we got element 2. Because it has the lowest first ionization energy, and it's easier to take up the electrons like that. Yeah, that's it.